welcome back to my limit series. Today, I would like to prove that differentiability implies continuity. That being, if we have a function and the derivative exists at that point, then therefore the function is also continuous at that point. For an intuitive understanding of this idea, I would recommend you to think about this for a little bit. But this video will be focused on proving this idea. So why don't I write this rigorously? So we can say that there exists a real number L such that the limit as x approaches x naught, where x naught will be the point of differentiability. So we have f of x minus f of x naught as our change in y, and x minus x naught as our change in x. And we're looking at the limit as x approaches x naught. So these 2 points are getting closer and closer together. This is a slightly different limit definition, or derivative definition, from my last video, but this also conveys the same idea, which hopefully has been communicated. So we assume that this limit is equal to L. So if we assume this is true, then we want to show then our function f of x must be continuous at x naught. But of course we can describe continuity using a limit. So we can say the following, that the limit as x approaches x naught of f of x is equal to f of x naught. And that just follows with our definition of continuity and our definition of a derivative. So let's look at this first limit we have here. Right, we have our limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught. Now, what happens if instead of looking at the limit of this quotient, we instead found the limit of this quotient times the denominator? And the reason I'm doing this is we're trying to get to this limit as x approaches x naught of f of x. So hopefully multiplying by the denominator will get us closer to just isolating this f of x. So we're looking at this whole product. And so of course, by the product law, right, this limit is equal to the limit of this first term times the limit of the second term. So I'll write the limit as x approaches x naught of, well, x minus x naught. And then this whole thing is multiplied by L, right? So we have our derivative, which is equal to L, multiplied by the difference between x and x naught. And so, of course, we need to make sure that this limit actually exists, but we'll make sure this limit exists later. Now, of course, you're probably noticing that, well, we have an x minus x naught multiplied here, and we have an x minus x naught in the denominator. So theoretically, right, could we cancel these terms out? Because, well, it's equal to 1. And we can. And the important thing to note is that x is approaching x naught, but x does not necessarily equal x naught. If you look at our limit definition, which I'll link below, right, we have 0 is less than the distance between x and x naught. So we can actually cancel these terms out, since x doesn't have to be equal to x naught. So really, this is also equal to the limit as x approaches x naught of f of x minus f of x naught. So let's really focus on this last part of this equation, where we have these two limits that we know are equal to each other. So if we look at this limit, the limit as x approaches x naught of x minus x naught, what would we think that is? Right? You'll probably look at it and say, well, we could just simply plug in x naught for x. Right? X is approaching x naught. So then surely that would be 0. And it is 0, but let's prove this idea. So we want to show that the limit as x approaches x naught of, well, the difference between x and x naught, we want to show this is equal to 0. So using the definition of a limit, what does this mean? For all positive epsilon, there exists a delta that's also positive because delta is a distance, such that whenever x is within delta of x naught, so 0 is less than the absolute value of x minus x naught, which is less than delta. But this implies the difference between our function, x minus x naught, and our limit, 0. We want to show that this is less than epsilon. So how do we show that the difference, or how do we show that the absolute value of x minus x naught minus 0 is less than epsilon? Well, we do this. We suppose our delta is equal to, what should our delta equal? Let's say our delta is equal to epsilon. So then, the absolute value of x minus x naught is less than delta, which is equal to epsilon. So the absolute value of x minus x naught, which in turn is equal to the absolute value of x minus x naught minus 0, these are simply equal to each other, is less than epsilon. And therefore we have proven, right, that this limit right here is just 0. So therefore, if we look at this equation that we have, right, we get 0 times L is equal to the limit as x approaches x naught of f of x minus f of x naught. So to summarize so far, we have that the limit of the difference between f of x and f of x naught is equal to 0. So we've shown this, but of course what we want to show is the limit as x approaches x naught of f of x. But first, let's just look at what this means. What information do we have here? Using the definition of a limit, right, we know that for all epsilon greater than 0, there exists a delta, and since we know what the delta is, we can just call this delta A. And our delta is a distance, so the distance is positive. And then whenever x is within delta of x naught, so 0 is less than the absolute value of x minus x naught, which is less than our delta A. But this implies here that f of x minus f of x naught, which is our function, then minus the limit, so minus 0, is less than epsilon. So we have this information, and of course what we want to show, and I'll write it in blue because we haven't shown it yet, is to show that the limit as x approaches x naught of f of x is equal to f of x naught. Now, of course, what does this mean? Well, it starts off in a lot of the same ways. So for all epsilon greater than 0, there exists a delta greater than 0, such that whenever x is within our delta of x naught, that this implies that the distance between our function and our limit, so absolute value of f of x minus our limit, which is f of x naught, is less than epsilon. So to show this, right, we have to figure out, well, what is our delta? And let's suppose that our delta is equal to our delta A. So we get access to this information, because this is what we're using to prove it. So we suppose delta equals delta A. Therefore, we know that the absolute value of f of x minus f of x naught minus 0, and this will equal to the absolute value of f of x minus f of x naught. And we know that if this is less than epsilon and this is equal to this, then we know that this difference is also less than epsilon because of the property of things being equal to each other. Therefore, that's what we want to show. So the limit as x approaches x naught of f of x is equal to f of x naught. Therefore, the point is continuous, meaning that if we know that the derivative exists, that is enough to show that there is continuity at that point. And therefore, differentiability implies continuity. Thank you very much for watching.